but to do problems which will need the kind of things we have been looking at, okay, in the last class. But yeah, but they're just more like, you can just treat them as independent problems to start with. Let's see. So the first problem, the theme is allocation of classes. Okay, classes. Before I state the problem formally, okay, first of all, can all of you see the screen? Okay, right. So allocation of classes. So what is it? What is the context? I think that's important to know at this stage. So the situation is like this. Okay, so say you have a school. Okay, and you have several classrooms. Okay, let's say you have these classrooms, 7 classrooms. Okay, maybe I should 7 classrooms. So I'll write it here. So classrooms. Now there are some classes running. Okay, let's say 10 classes. Let's not go so high. Let's say 5 classes. Okay, 5 classes running. 5 classes means 5 different courses, you know, or 5 different, yeah, courses. So that's to distinguish it from the class. Now, the timings for the courses are as follows. Timings. Okay, so let's give them names, not a problem. So let's say mathematics, and let's say the timing for this is 9 to 10:30. Okay, and let's say there is physics, whose timing is 10 to, yeah, maybe this should not be 10. Let's say the timing for this is 11 to 12. Let's just a 1 hour class. Okay, and let's say, yeah, something like some art class. Okay, and let's say its timing, it's 10 to 11:30. Okay, and we have a 4th class. Let's say we have a history class. So the history class is, let's say, 10:40 to 11:15. Okay, and then there is a 5th one. You can take it biology. And let's say the biology class is from, okay, let's say it's from 12 to 1 p.m. Okay. So here are the 5 subjects, and here are the 5 timings. Okay. What is it that we want to do? Okay, before I say that, certainly I cannot run 2 classes or 2 courses in the same classroom. Right? I cannot run 2 courses in the same classroom if the timings overlap. I cannot do that. Right? For instance, I cannot run maths and arts at the same time in a class. Is that clear? Yeah, because their timings are overlapping. I mean, yeah. So I can write that as a condition. Okay. Only one course in a classroom at a given time. Okay. Yeah, that makes sense. What is the question? The question is, what is the minimum number of classrooms required? So all these conditions are natural. There is no mathematical condition. This is just practical conditions, right? What's the minimum number of classrooms required? This is a dummy example for some theory, But we are not going to do the theory today. Today we're just going to look at various problems and get a feel of what theory should be learned later. And if the question is not clear to someone, they can say. Maybe I should call this classrooms. So for instance, for maths and arts, we will definitely need two classes, two classrooms. We'll need two different rooms. But then overall, how many rooms do we need minimum? And otherwise, you can use all the 7 rooms. You can just assign, yeah. Okay, so you're saying 3 classes is the smallest. Okay, let's see. Others have gotten any numbers? Yeah, Manu, how many classes do you think? I mean, you don't have to get the minimum. Yes, any number will. You think? Can you repeat? 3. Okay, let's see. Manu, have you tried? How many classes do you think you will need? Certainly, if 5 classes will be enough. But can you do? How many classes do you think you can use? Yeah. All right. Okay. So let's see. So let's say we hold. Let's name our classes. Okay. So let's call this classroom 1, classroom 2, 3, 4, 5. Okay. Then we have classroom 6 and we have classroom 7. So let's say since mathematics is the earliest, we can put mathematics in classroom 1. Okay. We can put it in classroom 1. Is that okay? Right. Then because physics is happening at a time which does not overlap with the timing of mathematics, we can also put it in the same classroom. Okay. Now you have arts. This arts, whatever. Okay. Can you put it in classroom 1? Manu, can you put arts in classroom 1? Okay, but look, the timing is overlapping with the timing of mathematics, right? Like the mathematics class would have not ended. Is that right? The mathematics class would have not ended. It will go until 10:30, so we cannot start the arts class at 10 in the same class. Is that right? Right? This is not possible. There are two classes at the timing. This is what I mean when I say the timings are overlapping, right? The arts class will start at 10, but then the mathematics class will still be going on. So you cannot put it in the first room. So naturally, our instinct will be to put it in the second room. So this is just we are trying to find the best possible. This may not give us the best possible answer, but this is the way we are going. Let's see. Since this is a small example, so maybe this will give us the best answer. Okay. Now, what about history? Can you put history in classroom 1? Let's see. Can I put history in classroom 1? See, mathematics has no problem with history, okay? Because its timing, it starts from 10:40, and by that time the maths class would have ended. But I cannot put history in the first class for the reason that the physics class overlaps with it. This is the problem, right? I've already decided to start the physics class at 11. So the history class cannot start at 10:40 because the last 15 minutes it would still be going on then, if right. So it's not possible. So the history class I have to put in a separate class. So again, just going through it, very, because it's just the first example. The history class, can I put the history class in classroom 2? Exactly, right. So I cannot do that, right? And so you see the history class is overlapping with the arts class. These two timings have an overlap. So the history class has to go to some other room, right? So that has to have a separate thing, third room. Okay. What about the biology class? Well, the biology class has nothing on anyone. It's no problems. You can just put it anywhere. So you can put it anywhere means you can put it in anywhere. So you can just put it in classroom 3, right? And this is cool, isn't it? V3. So it seems like this is the minimum. And I mean, if you're on a test, maybe you can just write it. This is the minimum. Okay. Right. So I hope everybody has understood. So you have to just go one by one, and you have to just figure out what's the best you can do for that subject. I mean, what's the best you can do for that subject without introducing a new classroom, without opening the door of a new classroom. Okay. Let's say that's the costly thing. So you have to open it, clean it up or something. Something. Yeah. Yeah. Anyways. Right. And so the reason why I did this problem is because this can be, I mean, that's really the merit of it. Because, I mean, analyzing this situation this way, okay, where you have, it's quite, problematic in the sense that every time you have to look at what overlaps, and not look at, but you have to read, right? Every time you have to read what overlaps and what doesn't overlap and so on. And if there are 100 subjects, I'm just saying, if there are 100 different items in this thing, then there will be a problem. So we want to model it. The other reason why we want to model is that really most of the information, these names of the classroom and is useless. That's number one, right? The names of the classrooms is useless. And number two is that the amount of overlap is useless. Does everybody agree with that? The amount of overlap is not an important information for us, right? Now the maths and physics, sorry, that's not overlapping, but the maths and the arts is overlapping by 30 minutes. But even if it overlapped by 5 minutes, it would still be a problem, right? So we just want to understand which ones overlaps and which ones don't overlap, right? That's all we are interested in. So we are interested in which subjects or which pair of subjects overlap with each other. Yeah. Which pair of subjects overlap with each other. If they overlap, then we have to give them different colors. We have to give them different classrooms. That is the thing, right? The amount of overlap, not important. So this is not the problem solving aspect that I'm discussing at this point. I'm discussing modeling a problem, removing the unnecessary details. And so you first realize what is really unnecessary in this problem. This is a simple observation, right? Amount of overlap is not important. Do the simple observations, and you see the modeling will be simple, but still, we can't come up with it on our own. I mean, at least I have I know this, so I can tell you, but this is a really good kind of modeling. So let me, okay, let's not remove that, right? Okay, let's still keep it, but let's keep it like this maybe so that we can, yeah. So here itself, I want to do the rest. Shifting it down. So you can guess what I'm going to do. For each subject, I will make a point. Okay. So for mathematics, I made a point. For physics, make another point. See, you don't even need to label these points by alphabets, but I'm just doing it because this is the first step. We're going. Then there's history, and then there's biology. Now again, how you put the points, what distance, what figure you want to get, all that again doesn't matter. Now, if two subjects, so if two subjects overlap, okay, right? If two subjects overlap, I draw a line between them. Draw a line between them. This is the rule. So let's see. So let's ask this question. So should I draw a line between arts and history? So should I draw a line between H and A? Yeah, should I draw this line? Yeah, we should, right? Because arts and history intersect. Right? So we'll draw a line between them. And so I'm just wanting to clarify the rule of drawing the line. So we can pick a color and draw the lines. So we can draw a line between arts and history. And similarly, you can know. So between maths and arts, I will draw a line because their timings overlap. Right? And between maths and arts. Does maths overlap with anything else? No. So that's okay. Then the physics. Now physics overlaps with history. So I can join it. Right? Does physics overlap with anything else? Yes, it overlaps with arts. So I'll join that. Right. And biology overlaps with nothing. So that's not a problem at all. All right. So now what should the problem be? What should the question be? Yeah. So now the question reduces to, I need to color the vertices. I need to color these points. Right? That's what I get, right? I need to color these points, meaning that coloring is now doing the role of assigning the classrooms. Okay. I need to color these points, color the points so that if they are joined by an edge, if they are joined by a line, which means that the timings overlap, then they get different colors. I'll remove it at this point. Then they get different colors. And that's different classrooms. So I have these subjects which are my points. Whenever two of them intersect, I've joined them by a line, which means that I need to give them different classrooms or different colors. So now the problem is just coloring this graph. So what is the problem now? We have these 5 points and we want to color them, give colors to them so that, in the good old way, you color them so that if 2 points are joined by a line, then we give them different colors. Okay. So then the question becomes the old question. Okay. Find the minimum number of colors for the graph. Find the minimum, smallest number, minimum number of colors for the graph for this picture. So this we have seen earlier, right? For example, if I color maths with pink, then the arts will need a different color. Is that right? Then I have to color it with. Now this is now it's very obvious now that we have understood the correspondence, but right. And of course I can color physics also with pink, right? Because they don't have an edge. When they don't have an edge, you can color it with the same color. For example, you can color this also with pink. Is that right? I can color the biology also with pink because it doesn't have an edge. Right? I can color history with pink as well. Is that right? Oh, sorry. Yeah, that's wrong. Yeah, sorry, that's wrong. Yeah. Otherwise, we'll just need two colors. Yeah. So for history, I need a third color, right? That's a good observation, right? So for history cannot be colored with pink or green. That's very obvious. So this needs a new color. That's the reason why we need three colors. But now the problem is much more elegant. Is that right? Problem is much more elegant, and it's also very clear now that we will need three colors. Can anybody give an explanation now as to why you cannot do it with two colors? I know that's little just it's very obvious, but still, can we give an explanation? So why two colors are not enough? And really explaining these things becomes easier through this picture rather than the picture of classes and that exact timings and so on. Why is it that two colors will not be enough? So yeah, this is just a matter of really saying it in a false proof, fail proof way. Like, so the reason should be that there's a triangle here, right? So whenever you can find a triangle in your picture, is that right? Whenever you can find a triangle in your picture, you cannot color that picture with two colors. Is that right? I mean, it is absolutely clear. It should be absolutely clear. I mean, this is because it is like a thing that a small thing that you prove and you use it in other big places. They could have a very big picture and very complicated and very big picture, like network, huge network, which you're trying to give colors to each of the points, and then to prove maybe that three will definitely not be enough. All right, to prove that you will need at least three, you just need to find out a triangle, right? If you can find a triangle, then you can say that yeah, two will not be enough, right? Because the triangle will need three colors. Is that right? Because suppose you have put a red here, then you have to put a different color here, screen, and then you have to put a different color, and really this is the only way. So finding obstructions is very important to get to say things like two will not be enough or three will not be enough. Finding obstructions, and usually there are simple obstructions that one needs to find, okay? Because there is a because there is a triangle, and you can imagine this problem would be very well handled. I mean, or I should say this method of modeling it in terms of points and lines would be much more fruitful, very fruitful, if if we had more subjects and so on, right? Because when you model it, then you can really see, you can see what things are there. And of course there are algorithms for finding these numbers and so on, but that's for later. Right. Okay, it's good. Now we will focus on special type of, graph. So graph that need two colors and need two colors. And we come to a problem through that, but let's first graph that need two colors, graphs that need two colors. So we have seen that even some very complicated looking graphs could need three colors, could need two colors only. So if the graph is complicated, you may think that you'll need a lot of colors, but it depends. You can still do it with two colors. Let's see. Let me draw a graph and ask how many colors are needed. So draw the graph. Four. And all right, let me just think of it. Right. Let's try to color this graph. How many colors are needed? Needed for this graph. When we know the rules, right? Just still write it. Okay. If points are joined by a line, then they must get different colors. So the goal of this is to show that you may have complicated graphs. I mean, give much more complicated example, but that case may be difficult. It will be difficult for us to figure out really. But this is slightly interesting graph, but it can still be done with only two colors. Okay, you were about to tell too. Okay, let's see. Manu, have you? Can you say what color? How many colors would you need? Or you can start coloring, and you will see how many needed, right? So let's see. So if I color this with blue, then what should you do next? So that we really, in organic way, come with the number 2. What color should you need for this? A different color, right? You need a different color. So that's pink. Okay. Then what about this one that I've circled, this third vertex? Can we color it with pink? No, right? We cannot color it with pink because there's a line joining them. Okay. So, but can we color it with blue? Yes, we can color it with blue. So we do color it with blue. Right? And similarly, this also we color with blue. Right? Now we move to next one, this one. What color should I use? Should I use blue, pink, or a different color? Right. See, you could use red, but because we want to minimize, okay, right? Because we want to minimize, so what is the minimum? Right? That's the goal, because maybe colors are costly to buy a new color. So you want to minimize. So that's why I will not use red, but we'll use pink. Okay? And pink is good, right? Because this point has nothing, doesn't have a line here. If there was a line there, then you would need a different color. That would be obvious. Then you would need red. But here we can do with pink. That's my point. I mean, you can put red. That's not wrong, but you can do with pink. Okay, let's come to the other points. What about this point? Certainly blue is out of the picture. Exactly, yeah, we can just do pink, right? And so it's, you see, it's a problem that when we start doing, we can just get to the answer. At least it seems like that, though. In These examples are created in a way that it seems easy, but in general, this problem of finding the smallest number of colors can be very hard. Means it can take a long time. Algorithmically, you have to analyze a lot of different possibilities, and there's really no fast way to do it. That's one of the problems in computer science. But that's fine. They are sure that we need two colors. Two colors. And you see, there was no triangle in this. That was our encouragement, maybe. There was no triangle in this. There was no cycle with odd number of vertices. Yeah. But one doesn't need to know the exact, one is more than knowing the exact reasons, one should be able to come up with the minimum number of colors to start with. Okay. So now my goal is to do this. Okay. What I really want to do is I want to partition this graph. I want to split this graph into two parts. So I want to have this first part, or maybe before anything, let me remove these things. And that's why I'm doing this question, because graphs which will only need two colors have a very special property. Okay, there's a very special way in which you can arrange such graphs. Before I do that, I think let's take another example. So if I give you this graph, and you can imagine this kind of situation can arise very frequently. So again, this is a complicated graph, but let's see. How many colors would you need for the lower graph? Okay, the question is how many colors needed? What's the minimum number of colors that one must use to color this graph successfully? Meaning that if if 2 points are joined by a line, then they must get different colors. I'm not writing the question. Smallest number of colors needed. Right. So if you have found two, then certainly that's correct. In the sense that certainly that's minimum. You cannot do with one color. It's very clear. Okay. So before I ask the exact scheme in which you went about it, is it obvious to everyone that it's two colors and not three? How can you explain it in an elegant way without actually going through the exact process of coloring? Is there an elegant way to explain it? Two colors. No, that is not the reason. So for example, if that is the case, then I give you one more point here. And now you can think again. How many colors would be needed? And before I go there, before we really explain the details of that, for a better feeling of this, let's take a smaller graph, something like this, of the same nature, and try to understand how many colors this would need. Okay, so that we can all get the feeling for this. Let's say this is the situation. Then, how would you get started with this problem? You would start by coloring a vertex, right? So you color this vertex with red. Now my question is, what color can you give to this one? The one I circled. Do you need a new color? No. You can just give the same color. So I can give this red. Right? Okay. Now, if I ask this vertex that I've circled, what color can I give it? Can I give it red? Absolutely not. Right? You cannot give it red. So, okay. So that's blue. Now, what about this last vertex? What color should I use? Right. Okay. You can use pink. But okay, my question, Manu, to you is, can you do it with red or blue? Would blue be okay? Would blue be fine if I color this with blue? Right, it would be right. Right. So I'll just do it with blue. So again, the only reason why I'm doing it with blue is because I'm trying to be minimalistic. I'm trying to do it with the least number of colors. That's the goal. And that's why this is a problem. Otherwise, there's no problem. Color it however you want. So means not however you want, but yeah, you can use as many colors as you want. So you can color it with blue. All right, now let's come to this one. The last vertex. What color can I use here? I certainly cannot use blue. Can I use red? So you must always ask. So here's the strategy. You must always ask yourself. I mean, probably you picked up the strategy already, but you must always ask yourself, can I use one of the colors already used? Right? Can I use one of the colors that is already used? Then you will, I mean, in easy cases, get the right answer. Right? It means that you'll get the minimum answer in the end. So you can use a red here. Right? That's clear. You can use a red here. Right. So even though this problem looks complicated, this instance of this graph looks complicated, still has a simple answer, and you can probably see some pattern as well. All the guys on the left have been colored with red, and all the guys on the right have been colored with blue. So maybe we can use this to see if you can color this with two colors, and then also maybe give an elegant explanation. I'll just say a few more words on this type of graph. So you can see this graph kind of has two pieces to it, right? Two parts. And there are two parts. There is one part on this side and the one part on this side, left and right. And you'll see the guys on the left side are friend. I mean, they really have no problems getting the same color. Is that observation clear to everyone? The guys on the left side, the points on the left side, really have no problem getting the same color. They have no lines between them. Is that right? No matter how complicated the picture is, right? The points on the left side have no problem getting the same color, right? And so that is probably one piece of observation that one can use. Points on one side, because there are sides to this. Okay, one side can get the same color. Because they have no points between them. Again, there is no definition of side yet. This is just the word I'm using because I think we can understand it. The exact definitions would be not do it in this class, because the point is to get intuition about these things. Okay. Now, can we give an explanation as to why two colors are good for this graph? That is the remaining graph, the question. And mm-hmm. 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 Hmm. Right. Right. So what can you say about the left side? The colors. What colors can I use on the? Can I do with on the left side? Yes. Exactly, right. So the thing is that we don't even have to do the analysis. We don't even have to. So when you find a graph of this kind, and many graphs look like this. They may not look like this initially, but they do look like it in the end. There are some theorems that one needs to know to be able to know if you can make a graph look like this. So now people can imagine that knowing whether a graph can be made to look like this by shuffling the positions of the vertices will be a good question, but that's a little difficult to do. But here, once it is shuffled and given to us in this way, there is no analysis to be done. There is literally nothing to do but just color the entire left side by red. But first, is it clear to everyone? If it's not, please ask why you can give the same color to all those things that I've given red color on the left side. Right? Because there is really no line, there is no problem between them. There is no line between them, so I can. There's no harm, right? Giving them the same colors. And then, by the same logic as explained, we can give red on this side. I'm sorry, blue. I can give blue on the right side. And this is perfectly, and even once you see it, when you step back and see it, it just makes complete sense, right? Any two things that are joined have different colors, right? And looking back, it was really not hard because, yeah, two colors you see, it's so simple, right? There are two colors, and this is certainly making sense. Is because they are in two parts, and such graphs are called bipartite graphs. Okay, so these are called, sorry, these are what are called bipartite graphs, and there are a lot of theorems and theory to check whether a graph is bipartite and other things related to it. But yeah, for us, we know that two colors are needed for them. It is very good, right? The complicated graph only needing two colors. You can imagine a lot of problems can be like this. Relations can be graph like this. Okay. Now the next thing is, so bipartite graphs or this kind of picture is a very desirable picture. Yeah, I think that we agree with that. Very desirable picture from the perspective of coloring graphs, from the perspective of coloring points, so that they can distinguish. They can be distinguished if they are shared by a line. So it's very desirable to come up with this kind of thing. So we will try to do that for this graph. Okay. So what is it that we are trying to do? So maybe I can just shrink this a little bit to create a bit of space. I didn't think it was going to be like that. Anyways, doesn't matter. I think it's still clear. Yeah. What is that I'm trying to do? I'm trying to convert this, or rather, I should the rearranging is the right word. Convert this, to a picture like this, where everything is on one side is just doesn't have anything between them. Let's do it. Then it will be more clear what the picture is. So what I'll do is I'll take the point 1. Okay, so this point 1 I have picked up and put here. Take the point 7. Take the point 3, so you know what I'm doing. Taking all the points with one color, that was blue, and putting it on one side. And suddenly they will not create a problem. So what have I done? I've taken all the points which had the same color and I put them on one side. They are not going to create a problem for the exact reason that they have the same color. Right? I mean, if you remove these points, you'll be left with an empty graph. There is really no edges between these points. They're like this. That's why you can give them the same color. You can give them you gave them the same color to start with because they had no lines between them. And this is how the picture would look like. And that's why you can just put them on a line like that. Okay. But yeah, just as a rule, you can just start with remember that all the points with the same color, you can put them on one side. And when you look back, it's very obvious. And all the points with the other color, naturally, you'll put them on the other side. 2, 4, 6. Now, we have to keep the same graph. We have to keep the same relations, right? Like 1 and 2 are related there in our picture, original picture. 1 and 2 are related here. So in my latter picture also, I must relate 1 and 2. I can't just change the graph, right? I can't just say that bridge did not exist. I can't do that, right? I have to keep the same situation and just rearranging, redrawing the situation that is amenable to my analysis and so on. So nothing is changing. Nothing meaningful is changing. And what is meaningful here, what is significant here is the relation. What two things are related, not the exact line length of the line and so on and so on. Yeah. So really, what matters is that for suppose you have these 2 points. What matters is whether there's a line between them or not. Okay. It could happen that this line was like this. Okay. So my point was that the empty space, the wording is not exactly, phrasing is not exactly correct, because you see, you can still see an empty space here, but still there is a line between this. There's a line from here to here. So you have to really, what is important is whether they are joined by a line. Is that clear with everyone? That's important. So maybe then it's good to draw a good picture that can tell you the truth immediately. Yeah. Right. Okay. So I'm just shuffling these things. That's the game, right? I'm just shuffling this picture here just to draw it in a better way. It's a better drawing for the. This looks like a very unordered, arbitrary. I'll join 1 and 2. Should I join 1 with anything else? No, right? Because 1 really doesn't have any other neighbors. Okay. Now, what should I join with 2? What should I join 2 to? 3, right? 2 is joined with 3 because that's basically I have to draw the exact same picture on the side, the exact same relations. Then you have 2 and 7, and so you just join them. Then you take 3. What should you join with 3? You join it with 4. Join it with 6. Right? Then 4 needs to join with 5. And is there anything else to do? No. This is it. You see, we have the. Oh, I have not joined 5 and 6. Sorry, yeah, 5 and 6 has to be joined. Yeah. Now, so these two are the same questions. These two are the same pictures. But looking at it on the right-hand side, you can say it in a second that it needs 2 colors. Whereas if you were on the left side and coloring was not given, you would not know. I mean, you would have to do some work, like we have to just do it and see. Yeah. Oh, so that's another. So you see, this was a complicated graph. Sorry, this was a complicated graph, but once you draw it like this, okay. So is it clear the way I'm drawing it, right? Because I know that there are two colors used. All the colors that had means all the points which had one color, like blue, I put them on one side. All the points of the other color, I put them on the other side, and I just went down. So you see, a graph that needed two colors, I was able to draw it in this way. Now, it is true that any graph that needs two colors can be drawn in this way. And you can probably imagine how. But just think about it, okay? So the question is, any picture, any graph that can be colored with two colors can be drawn in this way. You can just put everything of one color on one side and another color on the other side. You can see. But that's it. That's about it. Okay? That we can do at this point. There are other interesting things to be said, but we'll delay them. But now that we are on this topic of this kind of graphs, so we've naturally landed here. Okay. The question is, let's keep the same picture, and the question is, so um, so let's say these are all. So at this point, we don't really need the numbers. Let's say these are all the boys. So boy 1, boy 2, boy 3, 4. Say these are girls. Okay. And the question is, can each boy, so this is again an instance of a different problem, okay, but in the same kind of situation, this is just an instance. We are not going to prove anything significant today, just doing this instance and getting a feel of things. Okay, can each boy be, of course, uniquely, means yeah, in this situation, uniquely paired up with a girl? In this situation, in this particular situation, so is the question clear? So we want to pair up each boy uniquely with a girl, and we would also want the reverse that would automatically happen. You can see if this happens at all. Can this be done in this picture? So what do I mean by paired up? Yeah, yeah. So I should say the question is incomplete, though it was implicitly there, but it's incomplete. So paired up with a girl he prefers, yeah, or the girl, I should say, who prefer each other. Yeah, who prefer each other. Okay. And really, whether two things prefer each other, I have joined it by a line. Okay. So, for example, I have joined boy 1 and girl 1 because they prefer each other, because there's a line in between. Boy 1 cannot get matched with girl 2 because there's no line in between them, so they don't prefer each other. Okay. So, that is really the underlying situation. The pair of people who like each other can be paired up, but otherwise, obviously not. Right. Yeah. So, for us, another example is boy 2 cannot be paired up with girl 2. That's not possible because there is no line between them. Yes, that matters, right? Because that's really the fatal obstruction. So it is not possible. Yeah, it is not possible. I think maybe, yeah. So certainly you can't pair this up, right? I mean, if you don't even need these lines, right? You can't pair this up at all because you can't have different number of people on both sides, or at least the number of girls should be more than the number of boys. Is that right? So this is not possible. Not possible. Is that clear with everyone, right? Because if you were able to pair this up, then how would you do it? I mean, there are two boys remaining, but only one girl. I mean, there's more things on the left side. There's no way you can pair it, right? Certainly, it's not. This question was just a fluke question, not possible. But it becomes an interesting question if we, make a new. So we have the same number of girls and boys. Okay, so a pairing up would look something like this, maybe something like this. Okay, means for one girl there's only one boy that is in the end getting paired up with. Okay, right. And so now I'll draw a new graph. Hmm, 2. Hmm, yeah, right. Let's see. Can we? Is it possible in this situation to pair up each boy with each girl? So remember again, the condition is like boy one can only be paired up with girl one and girl two and nothing else. These are the only possibilities for him. Okay, and so on. So will such a pairing be possible in this case? Or let me change the question a little bit. Will such a pairing be possible in this case? Yeah. Certainly, yeah. You can certainly just pair it in the obvious way. So you can pair one boy one with girl one. So you can pair boy one with girl one. Oh, I'm sorry. This is not possible. Do you guys see why this is not possible? Right. Sorry. This is not possible. So let's say that's given. If you just show why this is not possible. So you see, it is not possible because there are two boys who prefer this. Oh wait, I'm sorry again. Let's think about this again. It's just messing it up. Sorry. See. So see, if you pair a boy one and girl one, then that's fatal. That's not good, because then whom are you going to pair up boy two with? Is it making sense to everyone? Boy two cannot be paired with anyone else. You can only pair with girl one. So this cannot proceed like this. So certainly you shouldn't do this. You should pair up B1 and G2. So you pair up boy one with girl two, and you pair this up, boy two with girl one. And naturally, I mean, it's obvious what to do from here. Boy 3 with girl 3 and boy 4 with girl 4. Yeah. So first of all, is it obvious I mean, not obvious, is it making sense what I did? How the pairing scheme is going? Yeah. Mean that I can only pair someone with someone if they have a line between them. Otherwise, it cannot. Maybe that's like knowing each other, preferring each other. So it is possible. I could do it. But then think about this maybe later on. Think about this. This is not possible. Here in this situation, whether it's possible to do it or not. Okay. Just think about it. Okay. So, and that is it for today. I plan to do a few more things, but we didn't get there. But I think it's good to go through the examples slowly and really understand things. Yeah, to starting. Okay. Um, Yes. So that is it for today. I'll give some problems, practice some. So there'll be one set of practice for us, which will be simple, just running through the concept, and maybe a few interesting problems also. Okay. Right. So that's it. If there are any questions. Okay.